Hello everyone, my name is Khalid Chtaibi. I am a PhD student in Qadiyat University. I would thank the community of the second international conference on the big data modeling in the machine learning to accept my paper ID119. And today I am very honored to share with you my presentation entitled Lattice Boltzmann modeling of MHD Rayleigh-Bénard convection in a square cavity filled with a ferrofluid. This presentation is divided into 4 parts. I will start by introduction, and then I will present mathematical formulation. Next, I will present result and discussion, and finally by conclusion. Natural convection can be occurs in a fluid layer due to a horizontal or a vertical temperature gradient. When the bottom wall is heated and the top wall is cooled, this last configuration is called Rayleigh-Bénard configuration. The imposed destabilizing temperature gradient will trigger the movement of the fluid as soon as it exceeds a threshold value of the temperature. Therefore, the phenomena of heat transfer by natural convection in a confined enclosures in the presence of a magnetic field is the subject of the investigation of a great importance because it's found in industrial and technological applications as geophysics phenomena, polymer technology, and purification of crude oil, and reactor cooling. The enhancement of heat transfer is often a goal in many applications have been experimented as partitioned cavity resonance phenomena resulting from periodic heating. To improve thermal physical property of the base fluid, a technique based on the addition of the solid particle of nanometric size, enhancement of a thermal characteristic. On the other hand, the magnetic nanofields have an inherent advantage compared to non-magnetic nanofields. The configuration adopted in this study is a square cavity filled with ferrofluid whose horizontal walls are subjected to a vertical destabilizing thermal gradient, while its vertical walls are thermally insulated and subject of the action of a vertical magnetic field. The numerical method used in this study is the Lattice Boltzmann method. This method is based on 2 main steps: collision between the fluid particles characterized by the left sides of the equation 1, and determining to describe the movement of this fluid particle towards the neighboring nodes characterized by the right side of the equation 1. The thermal physical property of the ferrofluid were evaluated using the following equation. The macroscopic quantities are calculated as follows. This figure shows a good agreement between our result and those obtained by Hasnaoui. On another hand, preliminary tests were carried out to appreciate the sensitivity of the result by varying mesh size. These results shows that selected grade 120 is enough to conducted the present study. Result and discussion. Effect of Hartmann number. This figure shows that for Hartmann equal 0 and Hartmann equal 25, the 3 types of solution are obtained. The bicellular solution is characterized by asymmetry regarding the vertical axis, while the monocellular and the tricellular solutions show a symmetry with respect to the center of the cavity. On another hand, the increase of Hartmann leads to a substantial reduction of the flow intensity. On another side, the flow intensity is influenced differentially by adding nanoparticle in the presence of a magnetic field, and its influence is more attenuated in the comparison with Hartmann equal 0. The figure 3b shows clearly that the temperature field changes strongly from one flow patterns to another, particularly in the central region of the cavity due to the interaction between the neighboring cells. Thus, the number of undulations exhibited by the isotherms increase in the horizontal direction with the number of cells forming fluid. Height transfer. It's seen in this figure that the addition of the nanoparticle loses its advantage from some threshold of Hartmann depending on the type of solution. Moreover, increase of the Hartmann have a negative effect on height transfer. Conclusion. The result presented show that up to 3 steady solutions were obtained for relatively low Hartmann numbers. The monocellular flow is less favorable to height transfer and transit towards the tricellular flow, some threshold value of the Hartmann number that depend on phi. Both bicellular and tricellular resist to the increase of Hartmann even when the role of the convection vanishes for the Hartmann numbers higher than 80. And thank you for your attention.